go to Natalie. Hi, Natalie. Welcome.
Hello. Thank you for
How are
having me.
you?
Good. How are you?
Good. We are super happy to have you here. We have a completely different topic now, but I'm so excited because I think it's a way to bring an interesting topic to many developers that sometimes we are a little bit afraid every time that we hear about AI, machine learning, or things like that. But first of all, I would like to know where are you now and everything about you. Could you please
I am
introduce
in
yourself?
my
Okay,
room.
that's a good point. I'm in the kitchen also, so it's like a bar.
No, I normally work from home, so actually I came prepared for the situation. This is my regular office. So I recently got myself even a improvised standing desk. Let's say it's 2 shelves from IKEA,
All
but it
right,
works
yeah,
really well. As a standing desk, yeah.
yeah. It's like a step by step. We are adding more things into our home office. It's
Yeah,
like everybody is trying to do their own workstation, even though that
yeah.
I didn't even have like a good microphone before, but right now it's like I'm thinking to buy a good microphone. Where are you
Yeah.
based, Natalie?
I'm based in Berlin,
Great,
and
Germany.
yeah, in Germany, and I might have a special guest. So I have a cat, and as you know, cats love shelves. So if you see Silent Tail here, just say hi to Java.
Of course. It's a special guest. Why not?
Java because she's her official color in her passport. So in Germany, cats have passports, and
Oh, wow.
its color is a chocolate brown. So she's named after the coffee beans.
All right. I didn't know that cat has passport. That's like a VIP thing. And could you please tell us about your role? Where are you working right now? Which are your day by day work?
I work for a NoSQL database called Aerospike, and I actually enjoyed the previous talk because it was utilizing so much of parallelism, and that's probably one of my favorite things. So back to university days, my major, so I studied computer engineering, and my major was actually parallel programming. So I studied languages like CUDA, which is NVIDIA's language. That's a topic I've been passionate about since forever. And my favorite language is also Go because it has such a good parallelism and concurrency and so much focus on the difference between the two. And I enjoyed this field very much. That's also why I chose to go to join to the Aerospike last year. That's a database that I used to work with as a developer. And when I decided I'm looking for my next adventure, I said, let's go work for this really cool tool that I like. So parallelism, everything, yes, absolutely. It's going to be a big focus of my talk as well.
Great, great. And also you're a Women to Maker ambassador, right? You work along with
Yes,
the community.
Maker is a program by Google developer groups. So that's the focus is to bring more women to the industry. But so I started the Berlin chapter in 2015. That's 1 year after the global program started. And we said from the very first day, we want to make the Berlin tech scene more diverse. So we're always open for people of all genders and of all backgrounds. And in the beginning, that was not completely acceptable, but now it's completely cool. But we're still happy to always have people from all backgrounds. And by now, many cities have many chapters of women tech makers. So if anybody's listening and looking for a cool meetup to join, I can recommend.
Yeah, I think that I went to one of your meetups, but just to listen, probably a long time ago when I just arrived to Europe, and one of my first cities was Berlin. So probably we
Oui.
even already met. So that's
Oui.
super cool. Yeah,
Was
maybe.
Berlin your first stop in Europe?
But I was women tech makers meetups like 2 years ago. But I'm pretty sure that you were already there. Maybe I didn't meet you in person, but whatever. It's okay. We are here all together in the cyberspace.
Yes. That's really cool.
Alrighty. So if you want to contact Natalie, it's the Twitter there, so you can follow her, and then the stage is all yours. So whenever you want, share your slides and good luck.
Thank you. All right, so unless you're saying something, I'm assuming you can see my slides, and in the slides you can see my Twitter as well as the Twitter of this meetup, as well as the hashtag for this meetup. And I definitely want to start by encouraging and saying anything cool you learn or see, please share on social media and please tag and tweet. It's even easier these days. And this is the Captcha challenge. And 2 years ago, I helped a friend to test a project that he was doing. So it's kind of like a mini CTF or capture the flag or a hacking competition for conferences to do between talks. And the way I was helping was to test the different stages and to see if it's realistic to do within the time frame that is dedicated for this. And this specific one was to break into this Captcha. And the way to do this is, of course, brute force. So try all the combinations from 0000 to 9999. It sounds pretty simple, but there's a Captcha text there, and then every time you need to have, if you don't want to type this and you want to brute force, you have to code this in some way. And so I used the Go programming language actually to do this, and it's indeed possible to do in a few hours. These were the steps that I did. So for the first step, you inspect the model. The model is the machine learning model, which was provided, and this was kind of the win from the previous stage of that challenge. By inspecting the model, you get all kinds of information, like what's the input, what's the output, format, and so on. Next step is load it into the code, and then try to log with the pin. So 0000 is the first attempt for the pin. And when you do this, you first of all open a cookie jar when you connect to the web. You get the Captcha image, you do the prediction using the ML, and then with the combination of the current pin, you try to log in. And if it happens that the prediction, sorry. If it happens to be that the Captcha is wrong, you fall back into step 2 and you have the open connection cookie jar, so you're still good. If you want to read about this or see the code, you can go to the blog post of the Gophers Academy Advance series. So this is something fun that the Go community has every December. Every day there's a blog post about some Go-related topic. And if you want to see the code base, this is the link on GitHub. I'm sure this will be either recorded or uploaded, or you take a screenshot. And the worst case, you can ask on Twitter. I will share the link again. But I am not a data scientist. I am not a machine learning specialist. I studied computer engineering, and I designed chips in Intel in my first job. I spent the last 5 years working in Go, and now I switched to do cool things in databases, still focused on parallelism. Still, I managed to do this really cool thing with machine learning, and all I had is my knowledge in Go. So in the past, I gave talks about machine learning and about Go and how you can use Go for things like system programming. And in this talk, I'm kind of excited to connect all the dots together. I will be describing the beginning of my journey in building an end-to-end machine learning from scratch based on the existing knowledge that I have, nothing else. Any machine learning engineers in the crowd, or web developers, or platform engineers, or DevOps, I hope there's a good mix in the crowd so that kind of between everybody together, the dots will be connected, because definitely a mix of skills could be helpful for this talk. And I hope that in the next 45 minutes, there will be those aha moments where something sounds familiar, and a lot of moments of like, wait, what? And I hope that by the end of the talk, you will leave the room with a little bit of understanding of the end-to-end, so really the full part of a machine learning production system, and the passion that's coming with, oh my God, there's so much that I don't know and I need to know. And the last 2 things, I will be asking questions. I guess it's hard to make this interactive, but if you sit at home from the other side of the screen, just say yes, no, and I'll imagine you're participating with this. And if you see anything cool, please share. I want to say that this is what you see on the screen is me as a gopher. The gopher is the mascot of the Go programming language, and there's a really cool tool that's called Gopherize Me, which you can go and build your own gopher. So what is a machine learning?
I think we missed Natalie for a second. Yeah, I think she's back now.
All right,
Yeah,
should I jump back?
Commercials, go back. That's it. You can go ahead.
Repeat the slide.
Yeah, if you can go to the previous slide, better, I think so.
Previous slide was what is machine learning then?
Exactly, that's where we stay. Okay, all yours.
I hope everybody has the time to Google. Basically, machine learning is the creation of algorithms which modify itself without human intervention when you produce the desired output by feeding itself through the structured data. It's a subset of AI. What is AI? Many things. This is a great picture that I got from Twitter. The handle is the Alex Freeman, and it kind of covers how AI is just a tiny bit of it is machine learning, and there's so many other things like NLP, and then intelligent robots, and computer vision, and supervised learning, and unsupervised learning, and text and speech, and planning, and scheduling, and whatnot. Wikipedia says that artificial intelligence by computer science is what machines demonstrate, unlike the natural intelligence, which is what us humans demonstrate. And at the birth of this field back in the 1950s, AI was defined as any machine that is capable of performing a task that would typically require human intelligence, such as learning and problem solving. Okay, so we know kind of what's machine learning, what's AI, what's the difference between them. How do ML? Those are generally the steps. First of all, define what's your problem. How do you define success? How do you measure it? For example, is success responding in under 100 milliseconds, or is it responding with accuracy over 99.9%? Then gather the data. If it recognizes numbers, don't include in your data set letters. If it recognizes English, don't include Vietnamese characters. Of course, there's also a trade-off. If you want to learn the handwriting of one person, you're probably going to be super specific in the data set, and then your precision is going to be pretty good, but it's not really a wide use case. If you want to, on the other hand, if you want to have the data of many people, so have lots of handwritings, it's probably going to be lower precision, or you'll need a lot of data. Then you prepare the data. You clean it, so for example, you remove 30 pictures, you pre-process it by standardizing the pixel ender at 0, kind of like in prediction, and you randomize. So if you do prediction of numbers, you don't want to always feed it as 0, 1, 2, 3, 4, 5 in the same order, because then the machine will always guess if this was 1, the next one must be 2. And you split your data set. You take 75% to be your training set, and 25% to be the testing that you use in the end. And then you choose a model. That's based on the learning task. Is it classification? Is it regression? Is it something else? And then you know the number of inputs, and then it can be multiple, it can be a singular, and then the possible number of categories is possible number of outcome options. So if it's hot dog or not hot dog, the categories number is 2. If it's digits, it's 10. If it's faces, it's a few billions. And then you train the model. You assign random values, you predict using your training data, you repeat by adjusting the weights. So you have this equation that has variables, and you start with something, and you make iterations. And whenever you add a new category, so another optional prediction, it's called retraining. Once you're done using the rest of the data, so the 25%, and you evaluate the model using the metrics that you defined in the beginning, for example, speed, for example, accuracy. Then you do the fine-tuning, which is touching the hyperparameters. It's different from step 5 by usually being more specific and sometimes manual. And if it doesn't work, you go back to a few steps. So you can land at step 4, where you need to choose a different model or change the input. You can land at stage 5, where you need to just retrain the model. And there's all kinds of tools that do it for you, like AutoML. Once you're done, you can go ahead and predict. TensorFlow. It's one of the cool machine learnings that does it. Let's give it a bit of a closer look. So TensorFlow is an open source software, even end-to-end platform, for machine learning intelligence used mainly for machine learning applications like neural networks. It's also really good for solving partial differential equations if the pattern of starting a guess and making adjustments as you take steps sounded familiar. This is the image of a physical tensor from physics. This is more complex than the mathematical one we're using here, but it gives you a good understanding of the concept. And if it sends you back to uni days, take a moment to smile and evaluate your life until now. So a tensor is a generalization of vectors and of metrics, can be of multiple dimensions, and you characterize that with 2 properties, the data type, so integer, string, something more sophisticated, and the shape, which is a number of dimensions and the number of values per dimension. And then our tensor flows. This part comes to describe that the graph or the model is a set of nodes which represent operations, and the data flows through those nodes undergoing mathematical manipulation. And at any point you can stop, evaluate, and look at the value of your tensor or of your data at any node of the graph. This is the meaning of the name TensorFlow. What I like about TensorFlow is that it's community-driven, and it's becoming really friendly for developers who don't have machine learning backgrounds. Some of the tools that do this are AutoML, where it automates a machine learning model design for you. Basically, you drag and drop pictures and tags, and it does everything for you. And there's the TensorFlow Hub, which is a repo for models. Basically, you're a PhD student who came up with a really new cool model, and if you want to share it with the world, what you do is you just upload it there, and it becomes accessible for everybody. It's all open source, and contributions are always welcome. Many languages are supported. AutoML is a tool we covered quickly, landing back right after this step. The TensorFlow Hub lands you pretty much in this step. Black book solutions that are built on top of TensorFlow, plenty out there, lots of cool stuff. The topic of our talk is the infrastructure, right? This is a really great article from 2015, and it's talking about all the potential issues behind quickly hacked machine learning systems. 5 years later, it's still pretty overlooked and very much relevant. I very much recommend to take a picture and to Google it later. Accessible for everyone. It's open, no need to purchase or any special connection to university or whatsoever. Take the time and read this. A production machine learning system involves a significant number of components. The algorithm is just one part of it. In fact, it's about 5% or less of the overall code of a production system, looking at it end to end. A production system devotes considerable resources to the input data, collecting, verifying, extracting features. And to add to that, a serving infrastructure, so presenting the solution, must be in place to put the machine learning prediction in practice in real world. We will now dive into the architecture components, and it's going to be a lot. Take a deep breath. Also good for the brain. Now, I want to say that as an engineer, I love giving practical hands-on advices in all of my talks. This means I'm going to be specific. I'm going to be specific about some tools that I'm mentioning. I'm doing my best to mention open source tools because it's great. This is by no means a comprehensive list, and there's many, many solutions out there and many other optional architectures out there. Let's start with a pretty common one, Hadoop. Probably some people here have heard this name, and if you're wondering what does the name stand for, it's High Availability Distributed Object-Oriented Platform. This is an Apache project, so this is the cool and the right logo to use with it. Apache Hadoop is a collection of open source software utilities that facilitate the network of many computers to solve problems involving massive amounts of data and computation. This is a software framework for distributed storage and processing of big data, and it's using the MapReduce programming model. This means this is a set of open source programs and procedures, and anyone can use this as a backbone for their big data systems. And it's made of 4 modules. Each one carries out a particular task, which is essential for this big data analytics. The first one is a distributed file system, which allows data to be stored in an easily accessible format and across different storage devices that are linked. Can be a very large number of those. Next is the MapReduce, which provides the basic tools for poking around in the data. It's named after the 2 basic operations the module carries out, map and reduce. Map is reading the data from the database and putting it in a format that is suitable for analysis, and reduce is performing the mathematical operation. For example, how many people under 30 are in the customer's database. Next one is Hadoop Common, which provides the tools you need for the operating system to read data that is stored in the Hadoop file system. And the last one is Yarn, which is managing resources of the system, storing the data and running the analysis. And it might sound familiar to you because some recent modern tools have been competing with it. And there are many other procedures, libraries, and features that are considered to be part of Hadoop and joined over the last few years. The flexible nature of Hadoop systems means that companies can use it freely. We said that. And it's widely used as even in about half of the Fortune 500 companies. This slide is probably the trickiest one in the entire presentation. I'm putting apples and pears together. To add to that, I'm going to blend in papples. If you haven't heard of papples, aka crunchy gold apple pears, aka nashi, these are the crossings of an apple with a pear. And technically, they're more of an Asian pear. Okay, so we have a disclaimer that we're going to be comparing some hard to compare things. Back to the slide. You can say that Hadoop is one of the platforms you can build a data lake with. If you're not familiar with the term, a data lake is a centralized repository that allows you to store all the structured and unstructured data at any scale. The data comes in all sizes and shapes, and you need different tools to make the platforms. Okay, so this is the big slide, and those are all types of tools you can build data lake platform with. Google BigQuery, Apache Hadoop, Apache Spark, Azure Data Lake, and many, many others as well. Those specific 4 all have Go clients. It's worth mentioning that as a big fan of the Go programming language, I'll be presenting how to do this tools, mostly focusing on Go. Next component is database. You can train models with data that you have in a folder on your machine when you learn to machine learning. But when you do this in production, you have lots of data. You need to share it. You need to have efficient access to it and organized one. That's what you use a database for. There's many options between SQL and NoSQL. Those presented for are all NoSQL databases, all have a Go client as well. Next one, function as a service, aka serverless, one of the coolest buzzwords of last year. And this means serving models to consumers. So you have your model ready and you want to let people approach it with data and get an answer. This is what this does. The model is deployed to a serverless service, which is being queried, and it's working both for online and offline servings, which we'll talk about. Then comes data governance. You want to make your data openly available. It can be internally across different departments. It can be externally because you want to contribute a data pool of open source data that people can use to learn or use for their machine learning models. So for that, you want to filter and mask the data. You want to make sensitive data accessible in a compliant manner. For example, GDPR, for example, data control policies, like each user can see what type of data. And there's an interesting open question here. Let's say you train data with some specific, you train the model with a specific set of data, and then you were required to pull out this data from your system, be it for GDPR reasons, be it for a client that moved, be it for some other reason. Is the model that is using this data, that's trained based on this data, is it still keeping it? Can you still say that you're meeting the requirements if you pulled out this data? Think about it. Next is monitoring. You can do this for model performance. Is it wrong, right predictions, how many of each? You can monitor your system performance. How many requests, what's the processing time, etc. You can look at the resource consumption and you can monitor your app. For example, what is the life of a transaction through the app, how many connections time out, and so on. And putting this all together creates what I see as a bare bones infrastructure. And I want to stress that this is very much my personal opinion. And I'm sure that if you Google what's the minimal thing you need for machine learning, you're going to get more than one right answer, and that's fine. That also many times depends on the use cases. Okay, so we have data, and we know that it comes in different types and shapes and formats, and it includes a lot of noise and a lot of bias. And it's important to do versioning of your data, same as you do versioning for the code, for reasons like we said about what happens if you need to pull data from the system. You probably want to pull it out also of your model. Deployed machine learning models are part code and part data. If you don't do versioning to that, means you don't do versioning to your model. Okay, so we need to make sure that we store in the system only what we're allowed to, like don't store credit card info if you're not PCI compliant. So step one, take the data, do some data governance and filter it. We've cleaned up the data, and now we can build our data lake where all the unstructured, unhierarchical, and unorganized data lives. You can also store it in the database or in an object store, like where you would store binary data like image, sound files, and so on. Then you want to make sure you control which user in your system has access to what data and make the data sets available for the different teams, like we said. So you do a second step of data governance. Then comes the training. Most common tools for that are TensorFlow and PyTorch, but there's many other tools as well. And it's important for me to stress that people have entire careers on this one square. Please be mindful of the simplification we're doing to be able to focus on infrastructure. Let's zoom in a little bit on the training. This is landing us to this stage of how to ML. And broadly speaking, there's two ways to train a model, a static way or a dynamic way. A static model is trained offline, which means you train it once with the data that you have, and this is your model. A dynamic one feeds on the data and keeps being updated as the data flows through. There's pros and cons for both models, of course. And the nice thing about a static model is that you make all possible predictions in one batch, you run it to the table, and then this basically behaves as a cache or as a lookup table. So it's easy to build, it's easy to test. The cons is that it can only predict the things we already know. So if you want to feed it with new data, you have to take it down, retrain, and put it back up. And the update latency can be really big. Dynamic model, we said, feeds on data that flows in nonstop, and the big plus of it is that it's adapting to changing data, so it's more likely to make better predictions. Let's take the example of a flower shop. You know that during the week you're selling this amount of flowers, as the weekend approaches you're selling slightly more flowers, and then comes February 12th, and suddenly more people buy flowers. February 13th, even more people buy flowers. February 14th, if by now your model didn't tell you buy double the amount of flowers, you're going to sell out on Valentine's Day really early and miss out lots of money. The cons of a dynamic model is, of course, that it can be compute intensive, latency sensitive, which means you're probably going to have to put some limit on your complexity, and you'll need to focus more on monitoring. Okay, so we have the model trained. What do we do next? Model is ready. We want to deploy. We want to serve it. So we say we do this as a function as a service. And this is coming with the entire CI/CD pipeline of testing, integration, and so on, and the whole web flow. And then you have an output, which is called the inference of the model. Let's focus on that. So this is landing us in step 8, which is the predict. And this can also be in two ways, online and offline. Offline means you take all the predictions in one batch and do this lookup. And online means that you predict on demand using a server. The big benefit of an online prediction is that it can make on new information, predictions on new information as it comes in, which, for example, bringing back to the example of Valentine's Day in a flower shop, great. But it is compute intensive, and all the cons we saw, this is you need to put more resources and you need to monitor them better. Offline predictions, you don't worry about the cost of that, and you are likely to use batch quota, and you can do a post-verification, so to ensure that for whatever input you try, you always going to have a reasonable output. But the big minus, of course, is that it can only predict things you know. Okay, so we have the inference and we understand a little bit better. Are we done? No, monitoring. Pretty important thing. We want to know the health of our system. We want to know the performance of our system. Now we're done. This is what I see as the bare bones architecture of a machine learning production system. If you want a slightly more detailed snapshot of the ecosystem, here's another piece of information about this. This is courtesy of Matt Turk, who has such a snapshot of the ecosystem for every year. And as you can imagine, every year, the categories grow and the companies inside each category grow. Zooming in a little bit on the different parts, there is so much that we didn't mention, like AI ops and data integration and data transformation, cloud data warehouse, data generation and labeling, and cross-infrastructure solutions and search visualization, security streaming orchestration, and even this list is not comprehensive. So to iterate that point, there are many things you can do in machine learning, and everything makes sense based on your use case. Let's talk about off-the-shelf solution. TensorFlow extended pipeline is a sequence of components that implement a machine learning pipeline. And quickly going over the different parts of this pipeline, example gen ingests and optionally splits the input dataset. Statistics gen analyzes and calculates the statistics for the dataset. The schema gen examines and creates a data schema. And the example validator looks for anomalies or missing values in the dataset. The transform performs feature engineering on the dataset, and the trainer trains the model. In the validation part, there's the evaluator that does deep analysis on the results. There's the model validator that helps you validate the exported models, make sure that they're good enough to be pushed to production. And the pusher pushes and deploys it on a serving infrastructure. Okay, now let's talk about a concrete example. This is a pretty huge company whose machine learning architecture I want to introduce. I cannot mention their name today, and I cannot mention their product because it will be a clear giveaway. So instead, I converted the example to spam emails. This is not something they do. Let's say I'm sending an email. Once I click send, some of the input about me is being sent to the system. It can be sender email, receiver email, title, content, header, footer, more information. This is the entry point to the system. This is sent as a web request. You can run this with the model as is, or you can add a lot more data points, like, has someone reported this user as a spam? Are there suspicious keywords in this email? But trying to generate this extra data is a pretty slow process. And if you want to be really fast, you're not going to be doing it like that. Especially if you want to have a lot of data points to make a pretty good prediction. What they do then is they run the few input data points through Aerospike, a NoSQL database that pulls out for each of the inputs the relevant information. For example, is this sender on the block list of anyone? Is this a new user? How many emails a day do they usually send? And so on. Information that they're pulling for the content is, are there some words in the content that are correlated with emails often reported as spam? Are there any too salesy words? And this creates the input feature vector. And in machine learning, an input feature vector is an individual, a feature is an individual measurable property or a characteristic. A set of numeric features can be conveniently described by a feature vector, and in spam detection algorithms, it's, for example, presence or absence of certain headers. Is the email structure more okay or more fishy? What is the language like? The frequency of specific terms, grammatical correctness, and so on. And so this is an example of how the email that I sent is being represented in the system after being pulled off all the extra data for the extrapolation that was done of it. And then from Aerospike, they get the input vector to the current email that we're inspecting and feed it to AWS Lambda. And then this is storing an in-house machine learning model that they have built with their in-house machine learning team. They built it using Python. The output is the percent of the chance of the email being spam or not spam. Based on the percent and all the dynamic threshold, this gets the category, should it be marked spam or not. Take a second to take this all in. That's a lot of information, I know. This is a pretty cool architecture. Of course, there's also monitoring on top of that. And it kind of reminds of the part of a backbones one. Taking a deep step. And we're approaching the end, so let's do a short recap of what we saw. We discussed what's AI, what's machine learning, and how to machine learn. This image or this representation is a good answer to what is AI. We then discussed shortly about TensorFlow, how this is basically an abstraction of information flowing through a graph or a model, which is a set of nodes or mathematical operations, and it's undergoing manipulation, mathematical manipulation. And this is this entire process of machine learning. We talked about training and inference type, online and offline. We talked one example of what is a bare bones architecture components. So we saw this. We saw also that there's this, which is a slightly more comprehensive snapshot of the ecosystem currently, and this will be way bigger in the years to come. And we looked at a concrete architecture of a production system using machine learning and Go, and this is how it looked. The email getting enriched, serving to a model, and based on the percentage of the chance of this being spam, it's getting the category. We saw that machine learning is about 5% or less of the overall code of a production system, end-to-end one. We saw that the input data is a big and tricky part of a machine learning system. And we saw what's an example of a bare bones flow. Process the data, store the data, train the model, serve the predictions, and monitor. And if there's 3 takeaways that I would like you to take today from this talk, it's this. If you're taking a selfie now with a picture with this slide of this is what you learned, next slide, you're going to get the handles that you can use on Twitter to tag this as, hey, this is something really cool I learned. And you'll also be trying machine learning infrastructure as your home project. These are the tags. And if you're interested in following the journey as I'm working on my own end-to-end open source example of a machine learning, please follow me. Thank you very much.
Oh, Laura, you're muted again. Laura!
This stuff of trying to pretend that I'm a YouTuber, it's hard. Like,
one day I will be watching the slides, we'll be watching the talk, and it will know, okay, now is the time to unmute.
Yeah. Yeah, thanks a lot, Natalie, for that. That was really, really useful, especially for me, because I'm interested in learning about machine learning, but also more, it's not my background, as you said. So it's a way to bring other developers, hey, you don't have to be a data scientist. You can also create cool stuff using machine learning. And something that I want to add is that in your case, we're using TensorFlow. So there is a way to bring TensorFlow to the web also, especially because we have some web developers around that is called TensorFlow JS. I don't know if you had the chance to work around TensorFlow JS or something like that, Natalie.
TensorFlow is awesome. It's good for work with JS. It has also embedded that you can use on tiny IoT things or on the phone. It's by now it's so comprehensive and covers so many use cases. I'm definitely a fan.
Exactly.
Yeah. Peter, who was a member of the team up until last year, did a blog post about a prototype that he built for computer vision using TensorFlow JS. Called Llama Vision, basically that uses TensorFlow to determine whatever the camera is looking at is in fact a llama, which I love. I love this use case. It's great. And it can tell the difference between llamas and other, similar kind of animals. I posted the URL into the chat as well. The other thing that, and by the way, I really, really enjoyed the talk as well. Thank you, Natalie. The other thing that I dug up, because obviously we just heard from Majid. One of the things we heard from Majid was about WebAssembly. I just dug up a project called Google Media Pipe, which looks like it's trying to take TensorFlow and or some kind of machine learning framework and bring it and implement it in WebAssembly as well. That makes a lot of sense to me. I don't know anything about it. I just know that I saw the website. But are you aware of other kind of projects like that are kind of like bringing machine learning into the web browser or into web applications?
That's the least of the experience I have with TensorFlow, unfortunately. If you had asked me about what interesting things can you do about that with mobile, I would be able to tell a little more.
Well, what interesting things can you do with mobile?
So good that you asked. So TensorFlow, you can have, it's called TensorFlow Lite, and it takes a model, it compresses it into a size of a few megabytes, and it basically is something you can run on any app. I guess it can make a good use case for progressive web apps as well, because those are the things that you want to keep light. So maybe this is a way to extend it to a web as well. I don't know if that's the intended use case. Worth checking for sure. So you can either have a model with TensorFlow Lite, either a model on your phone that you retrain, so what we said that was the online thing, or you can have it on any web server, and then it's basically serving it. And then this is definitely something you can do from any web, any progressive web app, and any app.
Cool.
I think a lot of
Thanks a lot. Yeah.
You talked about on doing stuff on devices. I think a lot of people are also looking to that kind of implementation as a way to preserve user privacy, because if you do the model creation and training on the, or you're doing you're storing the data at any rate. You're storing the data model locally. As opposed to sending it up to the cloud. And that can be one way in which user privacy
yeah.
Alrighty, thanks a lot, Natalie. I think we're gonna round up to don't make it longer, but again, we are gonna share our videos, also your slides, and we already share your Twitter here. So in order to say good night, we also gonna invite Majid. It's like my Spanglish, you know why, right? It's like, and also I think it sounds really cool, so I'm gonna try to call you.
Just say that then, if it sounds cool.
I need to put myself on mute every time that I So thanks everybody for being here and actually participate in our first YouTube streaming. We're hoping to have more of these conversations soon. We're gonna share these links, and yeah, thanks everybody for coming.
Thank you.
Thank you very much for arranging.
Bye everybody.
Bye.
Bye.